and then the IMPA, it's killed. So, just
But there is a...
okay.
No, it's plenty.
The CIRM and then the IMPA, the logo.
Uh-huh.
It's beautiful.
I thought you was saying that maybe I put anyone bad or something like that. Okay.
No. No,
No.
it's just the logos. Very nice.
Okay, so can we start?
Yes, I suppose.
Okay, so it's a pleasure for me to introduce Beatriz Molina-Samper from University of Valladolid, who will talk about local invariant hypersurfaces of holomorphic codimension 1 foliations.
Okay, so, well, thank you very much for the opportunity to give a talk and for organizing this beautiful course on foliations. So I want to talk about, well, it's a classical problem in the theory of local holomorphic foliations. That is the problem, we can say the problem of existence of a separatrix, we could say it. So it's about a survey that I have written recently with Felipe Cano. So just to set some notation, my ambient space will always be the germ of Cn at the origin, or a germ of analytic space along a compact that I have obtained by a sequence of blowing ups from there. I will work with a codimension 1 foliation that, well, locally, I always write things locally, is given by a 1 differential form where the coefficients have no common factor and satisfying Frobenius integrability condition. The singular locus is locally the zero locus of the common zeros of the functions. And well, we say that a hypersurface is invariant for the foliation if these conditions holds, but essentially means that outside the singular locus, the hypersurface is a union of leaves of the foliation. Okay, so the question it's a question attributed to René Thom. It's given one codimension 1 foliation, a local codimension 1 foliation. Is there an invariant hypersurface? And for dimension 2 is the Camacho-Sad theorem, but I think it's quite well known. For dimension greater or equal than 3, so in general, it's not true. We have some examples. And so that's for the dicritical case. In the non-dicritical case, there is a positive answer. And, well, in the dicritical case, although it's not true in general, we can ask for some families which have the property to have this. So there are results of Rebelo and Reis for foliations that are generated in dimension 3, for foliations that are generated by commuting vector fields, and also me with Felipe Cano work on the what we call toric type foliations, and for these families we have invariant hypersurfaces. Okay, so just to recall, in dimension 2, we say that a point is simple for a foliation if the Jacobian matrix of the vector field defining the foliation is non-nilpotent and has eigenvalues with non-negative rational ratio. When one of these eigenvalues is 0, we say that it's a saddle node. Otherwise, it's what we call complex hyperbolic. So it is known that there are only, in a simple singularity, there are only 2 formal curves invariant for the foliation, that each one is tangent to one proper direction of the Jacobian matrix. And the Briot and Bouquet result says that if the eigenvalue is non-zero, then the curve is convergent. So at a simple point, there is always a invariant convergent curve. Okay. Well, just to recall, this is an example of saddle node. Of course, the picture is a real picture, where we have the strong variety, so the associated to the non-zero eigenvalue is x equal to 0, and the weak variety is just formal but does not converge. Okay, so in dimension 2, the problem of existence of invariant curves is trivial if the foliation is dicritical, because in dimension 2, to be dicritical, it's equivalent to have infinitely many invariant curves. Being dicritical means that, well, at least in this case, that after a sequence of blowing ups, I obtain a component of the exceptional divisor that is not a leaf of the foliation, which is generically, where the foliation is generically transversal. And in the non-dicritical case, so the ingredients on Camacho's proof are reduction of singularities. So we have the Seidenberg result on reduction of singularities. Then we have the combinatorics of the Camacho-Sat index that allows to prove that there is a singularity that is not an intersection of 2 components of the divisor, where it is either complex hyperbolic or if it is a saddle node, the weak variety, so the one that can be formal, is hidden in the divisor. So I apply Briot and Bouquet to this point, I find the convergent curve, and I can project it. So this is more or less the idea. Okay, so in dimension 3, so just in dimension 2, the criticity is like the trivial case. In dimension 3, the criticity is going to give us an example of foliation where we have this invariant hypersurface. So I can start with this foliation. This is like the easiest Johann-Ulloos foliation, where I have seven lines of singularities through the origin. So it's a conic foliation, so when we blow up, we obtain a divisor that is like P2 and an algebraic foliation on P2. That is the restriction of my codimension 1 foliation to the divisor. And this foliation is known that has no algebraic invariant curves. So my germ of foliation in C3 cannot have an invariant surface, even a formal one, because otherwise the tangent cone of my surface will provide an algebraic curve on the foliation of P2. Okay, so let us see how. So to see how more or less the proof in the non-dicritical case works, I am going to introduce some notation. Okay, when I say that a vector field is tangent to the foliation, if it is in the kernel of the form, I call the dimensional type in a point the codimension of the tangent space of the foliation at this point. And So if I have a foliation of dimensional type tau, then it is going to be a foliation in lower dimension, a codimension 1 foliation in lower dimension, and analytically trivial along, so like a analytic cylinder in the other directions. Well, a normal crossings divisor is a union of irreducible hypersurfaces such that are given locally as a coordinate hyperplanes. And I will call foliated space to ambient space plus divisor plus foliation, just notation. Okay, so dimensional type 1 means just that my foliation is regular, so I'm in a regular point, and the unique invariant hypersurface passing through this point has normal crossings with the divisor. So the other, if my hypersurface is this one in red, x1 equals 0, or here in green, my possible dicritical components are the other two coordinate planes. When the surface is in the divisor, I say it's a corner, otherwise I say it's a trace. So the picture for the intermediate dimensional type, it could be this one. So I have like a foliation in lower dimension and trivialized in this case in one direction. So I find there are so many invariant, so what is important for me is that there are so many invariant hypersurfaces as the dimensional type, and maybe all of them are in the divisor. I call this case corner, or there is exactly one that is not contained in the divisor that can be convergent or maybe not, but has some good properties. If it is not convergent, in this case, this hypersurface can be not convergent, but still it is what is called transversely convergent. So I have the possibility to move from the point P to close points around these yellow curves, and I still have a formal surface there. Okay, and just the maximum dimensional type, where I find the same. I have here that is dimension 3. I have either 3 invariant, well, the picture is dimension 3. Either three components of the divisor, or 2 and a new hypersurface. Okay. So I'm going to call to this kind of yellow subspaces that are intersection of my hypersurface that is not contained in the divisor and the other. I'm going to call them trace subspaces. Okay, so more or less this is the summary of what we have said. So corner subspaces are intersection of 2 components, and trace subspaces are codimension 2 subspaces of the singular locus that are just in one invariant component. So with that, I can, when I have a simple foliated space, so something that is desingularized, I can take what is called a partial separatrix, so a maximal union of these yellow curves, or yellow codimension 2 subspaces. And I know that there is a well-defined space, this that I call here H hat, defining at each point of my partial separatrix a germ of invariant hypersurface. And I say that this partial separatrix is complete when this when this condition happens, but essentially it's that I have a closed immersion. My space is closed inside this germ. So in this case, the idea is that in this case, the space can be, the H hat can be projected by the singularization morphism, and I obtain something close on the, so if I have, so I have a foliation in the germ of Cn, I assume that I have a reduction of singularities. So any of these complete partial separatrixes, I can project if they are complete, if I have this closed immersion, I can project the space to obtain an invariant hypersurface for the original foliation, because the reduction of singularities, the composition of blow-ups, it's a proper morphism. Okay, so in a non-decritical simple foliated space, each partial separatrix is complete, and moreover, we can guarantee that there exists a point where it is convergent, and so everything is convergent in this separatrix. This is using a transversal, so here we take a transversal section in the sense of Mattei and Musu, and so we apply Camacho's theorem in dimension 2 to this transversal section, and that allows to find the point before. So the K point in the proof of Cano and Serrault in dimension 3 is that they prove existence of reduction of singularities for this non-decritical case. So for Eiger dimension, the techniques are quite different. So the techniques of Cano and Mattei are different because they there is no reduction of singularities. Okay, so any non-decritical foliation in the germ of C3 has an invariant hypersurface. And how much time I have? Sorry. What? Ah, okay. Perfect. Okay, so we can try to extend this technique from the non-decritical situation to the decritical one. So in order to see what things can happen or what things cannot happen in order to have or not invariant hypersurfaces. So we can connect these curves or codimension 2 subspaces of singularities that are like the drawn in yellow. We can connect them through codimension 2 subspaces contained in the critical components. Okay? So we define a extended partial separatrix as a maximal union of these trace subspaces that can be formed with singular points or also with regular points, but it must be finite. So the idea is that these extended partial separatrixes are going to be like this, the natural support of a, so if I have a hypersurface for my foliation in Cn, and I assume that I have a reduction of singularities, and I look to my hypersurface after reduction of singularities, so it is going the picture that I'm going to see in the exceptional divisor is this is one of these extended partial separatrices. And the idea is that, so again, if they are complete, well, there these extended partial separatrices, and they are complete in the sense that if I have the hypersurface, it continues being a hypersurface after reduction of singularities. So the idea is that I have also the reciprocal. If I have one extended partial separatrix that is complete, I have this space, this closed immersion, and it projects into a hypersurface. So I have like this projection, right? But now I find like two obstructions to have completeness for the extended partial separatrix. So one obstruction is like in the Joannulus example, when we have like, so it's this one. When I found my critical component, here I have like the local picture, I find an invariant, so locally an invariant curve for the restrict foliation, but it is not algebraic. It is not algebraic, so I cannot prolongate it. So the partial separatrix consisting on this yellow curve is not complete. Yeah? Because when I see the intersection with the divisor, I see this like this purple part that does not belong to my partial separatrix because it's not a global curve. And well, this is not the best picture, but another thing that I think that can happen, but I haven't had examples for this situation, is that we can find like two critical components together and even have them plenty of rational, of algebraic curves, maybe because I have rational first integral in each of one, but that they are forming like an infinite change. So I think that this can happen, but I haven't had any example. I don't know how to build an example or how to prove that this cannot happen, or how to prove in which situation that can happen or not. I don't know, but it's another possibility to have this problem of non-completeness. Yeah? Okay. So, well, just as I said, in the foliation that we call toric type means that the singularization morphism it's toric. Okay? So it's a sequence of blowing ups where, for example, in here I only can blow up either the point or the intersections of the divisors. And so here I repeat the situation. So in this sense, the desingularization morphism is a toric morphism. For this reason, we call these foliations toric type foliations. And what we prove is that in dimension 3, for these foliations, we have invariant surface. And the idea is that, well, we fix a combinatorial reduction of singularities, so a reduction of singularities done with this kind of blowing ups. And what we see is that the extended partial separatrixes that we find, so they having these prolongation obstructions. Yeah, so because the dicritical components that we find, they are all toric surfaces, and the foliations that we are considering have some algebraic curves that are the ones that we need. So, and moreover, so I try to do here a picture. So I imagine that this first curve is like a curve of singularities. I have the surface there. I can prolongate this hypersurface along this global curve contained in a dicritical component. And this point is again a singular point. So I have, in the cases where what I'm interested, I don't find two dicritical components together. More or less is the idea. Okay? And of course, we prove that there is at least a point where this, at least one singularity of this type, such that I have this convergent hypersurface. Okay, and just to finish, so what can we expect of a foliation without invariant surfaces? So there is this question that is like a local version of Brunella's alternative that exists for P3. So this is like a local version that says that, okay, if I haven't have an invariant surface for my foliation, then each leaf of the foliation should contain at least one curve, so one analytic curve. And well, this result is solved for some families of foliations, but it's an open problem to work in. And thank you for your attention. Sorry if I was a little bit messy.
Thank you very much. Are there any questions? Yes.
It's just about the previous slide when you talked about toric type. Sorry. So when you say that the reduction of singularities is given by a toric morphism, just one is needed. It's not a composition of toric morphism. Is it what you meant?
Well, so what I do is a composition of blowing ups.
Yes.
But this composition of blowing ups is a toric morphism.
Okay. So yeah. And the second question is, when you say that it is a reduction of singularities, what do you mean for a foliation defined on C3? What do you consider to be desingularized in C3? That all the points of the foliation are what we call simple points. So there is a notion of to be simple, as in dimension 2 for Eiger dimension. So it means that so all the points are simple.
Thank you. And also in that case, so there is no dicritical component. So what is, because the dicritical component were the problem here.
Yeah, we have dicritical components.
I have lost what do you gain in the toric type?
So what we gain is
avoid complication with the dicritical components.
When we find, so here in the picture I have like a dicritical component. So when we find a dicritical component, the foliation, the foliation in, so the divisor, well, when I find a dicritical component, a global dicritical component, it is a toric surface.
Okay.
And the divisor is the one given by the action of the torus. Okay? And what we prove is that the foliation defined on this toric surface has a global, well, when there is a singularity that is isolated, or an isolated invariant branch, this can be prolongated to a global. It's contained in a global curve. So the surface that I have continuous. It's not. So it's
Okay.
more or less.
Thank you. George? George, I don't hear you.
Oh.
Wait.
I think they have the micro.
There is something bad with the microphone.
But here there's a sign. Says maybe they
No,
have
it is not
closed.
this one.
Ah, okay.
We have a problem with our... Non, j'ai un message d'erreur. J'ai un message d'erreur sur l'audio et on les entend pas. We have to arrange something here. We have lost the sound. J'ai détecté votre haut-parleur, vérifie que le haut-parleur est connecté correctement. Il y a un message d'erreur. Impossible de détecter votre haut-parleur, vérifiez que le haut-parleur est... Non, c'est là, c'est ici, un message d'erreur. Non, j'ai ça, c'est différent.
Test. Test.
Message d'erreur. Georges, tu peux parler?
Test.
Allô, allô.
Ah, no.
Right. Okay. So, do you have any question?
We already clapped.
Ah!
We
So,
even tried to
please.
push harder than usual to see that Beatrice could listen.
So, let us thank Beatrice again. Okay, so we go back in